All right. All right, so let's get started. I suppose it's time now. Gives us about half an hour, maybe a little less. Okay, so because I don't know if you guys have the book yet or not, or maybe some of you can access it with, its PDF version of it online somewhere. But I couldn't, so I had to buy it. This is chapter 14, okay, which is fluids. Okay. All right, so if you remember, so far in other courses, we've talked about mass of an object, its velocity, gravity, speed, acceleration, and you probably had all sorts of electricity and magnetism, which had nothing to do with any of that stuff. It's all about electric field, force on a charge, and things like that. Now, everything we did in those cases were pretty much done on solid objects. Okay, so now, and with solid objects, with solids, we talk about mass and force. Okay, so we did this thing in 2a and 2v. Okay, mass, there's this many kilograms, there's this force, find the acceleration. Or there's this charge, and it's in an external electric field, find the force on it, and what is the acceleration on it, and so on and so forth. But now we're going to start talking about fluids. Fluids are, so with fluids, now of course with fluids, examples of fluids are, gases, liquids, and things like that. And you can't really talk about mass and force. So we can't really talk about mass and force anymore. We talk about some other things. We talk about pressure, P, and density, rho. So for fluids, it makes so much more sense to talk about pressure of the fluid or the gas or the liquid and its density, because air is a fluid. If you want to calculate the mass of it in your room, you can go and do that, and we'll do that a little bit later. But air is such an enormous penetrating fluid into our lungs and goes out the window, goes up in the air, airplanes fly through it, and then it comes back down and goes into an elephant's lung somewhere in Africa. So you can't really talk about the mass of this thing unless you really talk about the entire mass of the air contained within the atmosphere of the Earth. So it makes so much more sense if you're locally in a laboratory dealing with air to talk about its pressure and density rather than the mass of it, which is pretty weird to talk about. Unless you bottle it up into a container or a balloon, then you can talk about its mass, total mass, as well as its density and pressure. And of course, temperature is another factor when you talk about fluids as well. Okay, so what are some examples of fluids? Okay, so if you're talking about gases, then obviously, air is one. Oxygen forms a gas. that's O2. Nitrogen gas is N2, so on and so forth. And liquids, obviously water. I don't know, gasoline, olive oil, you name it, motor oil, antifreeze, and so on and so forth. Okay, now we talked about, when you're talking about fluids, talk about two things. One, pressure, which is defined as, you know, we normally write it as P, and pressure in a fluid, you can measure the pressure of fluid by measuring the amount of force it applies on a given area. So pressure has units of force over area. The units, now I don't know if you're familiar with this, what the brackets means. Brackets mean units. So unit of pressure obviously is unit of force. Divided by units of area, this is newtons per meter squared. All right, so we actually do have a name for this unit. This is called Pascal. Okay, Pascal is unit of pressure, which just means newtons per meter squared. Okay, so the fundamental equation of pressure is this. It's the amount of force per unit area. Force per unit area. Okay? All right, so in other words, if you are going to measure the pressure of a fluid, you have to find a device that you can measure the force on it for a certain amount of area that you've designed the device for, and you submerge it into that fluid and see what amount of pressure, what amount of force you're measuring, and then you divide that by that number of the amount of area the force is being measured on, and then you will get the amount of pressure. So one way the book shows is that this is one conceptual device to measure pressure. Okay, so you can have a some sort of a cylindrical shape container, and then you would have some sort of a piston, and you can just put a spring here. So that's a spring with constant K. This is a piston, and this is some cylindrical cup. All right. Now, what you're going to do is you're going to pull a vacuum from in here. Vacuum. Okay. So this device can measure pressure for you. The way it works is this. If you just hold it like that, you can just find out where this position of this piston is with respect to the cylinder. And because the atmosphere is going to put some pressure, there's pressure outside, that pressure is going to induce a force on top of this piston. That force wants to push the piston down because there is no force on the other side by any fluid. There is no fluid there. It's a vacuum. The only pressure is due to the spring. Okay? So if you find out how much distance that piston moves, you can go ahead and calculate the amount of force that pushes that piston down, and by equating that force with the force of spring, you can then go ahead and calculate what the pressure outside was. So this is a piston of area A. So you can always, in static mode, the force on the top has to be equal to the force of the spring. Now, of course, force on the top is equal to pressure times the area, and force of the spring is equal to K delta X. And so if you know K, you know delta X, and you know the area, you can calculate the pressure of the atmosphere. I'm sorry, that's area. Okay. So that's one quick and dirty way to create a device that measures the pressure or atmosphere. Because we know pressure is force per unit area. That's pretty much what this thing means. All right. So let me give you some examples of pressures in different places. Here's some pressures. This is atmosphere at sea level. Okay, atmosphere at sea level is 1 times 10 to the 5 Pascal. All right. A typical tire pressure inside is twice as much. Okay, that's a typical tire pressure inside a car. Okay, now we can get larger. Center of the Earth. Okay, center of the Earth, pressure is quite high. 4 times 10 to the 11 Pascal, roughly. And we can even get larger than that. Center of Sun. Okay, that's 2 times 10 to the 16 Pascal. So you can see pressure in the atmospheric pressure where you and I are in right now is roughly 1 times 100,000 pascals. Okay, which is still pretty large. And the question is why we don't feel it. All right, so that's some of the pressures, just so you have a gut feel for when somebody says 100,000 pascals, you say, oh, that's the atmospheric pressure on Earth at the sea level. That's just a roughly how we build up intuitive feeling for what Pascal measurement is. Now there are two more. There are a couple more. 2 more. Units of pressure in use. Okay, there's torr and there's pounds per inch squared, which is what a tire pressure is usually measured. You know, when you go and put it 32 pounds per inch squared, that's the second one you're using to tune the pressure of your tire. Now here are, and I'm sure by now you know what conversion factors are. So the way you build conversion factors are 1 Pascal is equal to 760 torr, and that's also equal to 14.7 pounds per inches squared. Okay. So, and of course, you can create your own conversion factors using this blue line down there. All right. So that's pressure, and in order to calculate to measure pressure, all you have to do is just measure force for a certain area, and then from it you can calculate the pressure. Now this is when the pressure is uniform. When it's not uniform, then things get more complicated, and we're not going to go over that. All right. Now let's talk about density. So much for pressure. Let's talk about density. Now density is written as rho, the Greek letter rho, and that's mass per unit volume. Remember, pressure was force per unit area. Now density is mass per unit volume for uniform density. Okay. All right. So let me give you some examples, some densities. All right. Again, air. Now we have to be careful with gases, and I'll explain in a second. Air at 25 degrees Celsius and 1 atmosphere of pressure. So density for air is 1.2 kilograms per meter cubed. You can see the units of rho is units of mass over units of volume, which is just kilogram per meter cubed. All right, so what does that mean? What does that mean? Air is 1.2 kilogram per meter cubed. What this means is if I had a cube that had 1 meter on each side of it, okay, so that's a 1 meter cubed, because 1 times 1 times 1 is just 1, and meter times meter times meter is meter cubed. So if I had a box that contained air at 25 C and 1 atmosphere, a box that had a height of 1 meter, width of 1 meter, and depth of 1 meter, that amount of air inside that box would weigh 1.2 kilograms. Okay? Weight, I should say mass. Whoa. Mass of air here is 1.2 kilograms. Okay? All right, so this will give you some feel for how much, how heavy is air. All right, how about water? Same, at 25 C and at 1 atmosphere. What do you think water is going to weigh? Very close to 1,000 kilograms per meter cubed. It's 1,000 times heavier than air, roughly. So if you had the same box of 1 meter by 1 meter by 1 meter, and you fill it with water, you would not be able to move that box at all. That box would weigh 1,000 kilograms, which is 1 ton, which is 1 metric ton, and it's 2.2 English tons. So that's a one heavy box. Simply by filling up a box 1 meter by 1 meter by 1 meter with water, you have 1,000 kilograms of water. That's how much more dense water is with respect to air. Of course, we can get higher densities. Iron is pretty heavy. Well, pretty dense, I should say, not heavy. So that's 7.9 times 10 to the 3 kilograms per meter cube. So you can see iron is about 8 times heavier, mass, more dense than water is. Okay. And of course, this thing keeps going on and on. You don't have to worry about it. But the thing that you want to take with you is one thing. Density of gases depends on pressure, temperature. Okay? So density of gases is not a constant. Okay? So you want to make sure you understand the density of gases is not a constant. And I'm sure in your chemistry class, you've learned that, PV equals nRT and how the density can be calculated at different pressures and temperatures and all that. So density is not a constant for gases. Now, on the other hand, for liquids, density is a constant. Okay? So density of a liquid is a pretty constant. The variation is very small. The variation with pressure, well, I'm just going to use P and T. Pressure and temperature is small. Okay, so you want to remember this thing so it doesn't come back and haunt you. For liquids, rho is a constant, and for gases, it's not. All right, so later on when we talk about pressure transmitting through a fluid from one side to another, the density of it is not changing, but you cannot say the same thing with gases. All right, let's see. All right, so let me now go over a couple examples. All right, so suppose here's a room. Here's a room, and let's give it some dimensions. 3 meters height, 4 meters width, and depth of 5 meters. A typical room is this kind of size. So let's calculate the mass Let's actually calculate the weight of air inside this room. Let's calculate the weight of the air inside this room. What do I need to do? Can somebody help me? Can somebody help me calculate the weight of the air inside this typical room? Anyone? What do I do, guys? How do I calculate the weight of the air inside this room? Well, how do you calculate weight of anything? How do you calculate the weight of anything?
You need the volume.
Okay, well, sure, but how do you calculate the weight of anything first? If I give you an object and I say, what is the weight of this thing? How do you calculate it? Yes, so weight is equal to mass times G. We knew this from a long time ago. All right, so all I have to do now is to find what? Because G is just G. So what do I need to do? I need the mass of the air inside the room. How do I calculate the mass of the air inside that room?
Is just the density of the air times the volume.
Density of the air, right, that's what we learned. Density of the air times the volume of the room. Okay, well, that's good. What is the volume of the room? Well, rho of the water, what was that? The rho of the water is roughly 1 times 10 to the 3 kilograms per meter cubed. And then G is G. Now I need the volume of the room. What is the volume of the room? That's right. 3 meters times 4 meters times 5 meters. Well, 4 and 5 is 20. 20 times 3 is 60 meter cubed. All right, what is the weight? Weight is 2, roughly 2 times 10 to the 6th newtons. All right. Now, that's a lot. That's a lot of newtons. In fact, if you divide that by roughly 10, you get the weight of the air inside that room in kilograms. That's a lot of kilograms. I'm sorry, I'm sorry, I'm calculating this from it wrong.
You used water instead of air. The density of water instead of the density of air.
That's correct. That's what I did. Yes, this is 1.2. Sorry, 1.2, and then the answer is 711. So, okay, sorry. And then if you divide it, that's still very heavy for air. If you divide that by 10, you get roughly 71 kilograms. So the amount of air inside your typical room size is 71 kilograms. It is the weight of a pretty good sized human being. And you wouldn't think that because air is so airy. So the mass of the air inside your typical room is roughly the size of a good sized human being. Okay, that is surprising. Usually when you first calculate a thing like this and go, wow, that much air is inside my room, that's amazing. Now, here's one other calculation we can do. Did we run out of time? Yes. So what I'm going to do is I'm going to get a print of this, of all the whiteboard stuff that I scribbled today and put it on Canvas for you, hopefully later today. so you know what we went over. We ran out of time. I'll go over the next example tomorrow. All right, guys. Thank you. Bye-bye.